minus delta concentration A upon delta T. T is time. Okay. So the change in the concentration of A over the time. Likewise, we have minus delta concentration B upon time, which is equal to delta P over yes. Okay. Now, why do you think that A and B have a negative sign? Exactly. Because their concentration is going down because they are being used up for the formation of the product B. So basically, if you're looking at a reaction rate, there is a certain amount of A being used up over a certain period of time, which is equal to the amount of B which is being used up because A and B are coming together. So only a known amount of A can react with a known amount of B, which ultimately is equal to the delta P or delta concentration P or the appearance of the product over that time period. Okay? This whole thing makes sense so far? Yes, no? Good. Yeah, because this is the point where I start getting confused. So just ask. Okay. Now, the other way we can write this whole thing, that rate is directly proportional to concentration A. Okay. And now, I have no idea as to why they ever decided to write F and G. Okay. But as you will read, you will find that F and concentration B raised to power G, okay, these numbers usually, okay, usually, not always, usually are equal to the coefficient of the reaction equation. Okay, so you can have something like 2A plus B is going to give you 2. Okay. So F in this case will be 2 and G will be 1. Okay. So the coefficient in the equation is written over here. But again, keep in mind that this is not the rule. Okay? But saying that is something that I need to tell you. So most of the time you will find that A raised to power F or B raised to power G is usually equal to the coefficient of whatever that reaction is. Okay? So now we have a sign of proportionality here. Instead, if we write that rate equals to A is the rate constant. Okay? Because you needed to change the proportionality sign. Okay? Okay.
Well, what did you say G was? I was writing that.
I mean, again, F and G is just two different notations. Okay? These are usually written here at this point if whatever the reaction equation is, whatever the coefficient of concentration for both reactant or both reactants and products is, you just denote them here.
Gotcha.
It's an F and G. Okay? Again, keep in mind, K is the rate constant. Okay? Now, the other thing that needs to be kept in mind is that the values of F and G, again, these are just told to you here, and again, you will realize that very soon that these are not really needed for you. But the fact is that you need to calculate F and G in an experimental fashion. These values, even though you're talking about coefficients in a reaction, these values still need to be denoted in an experimental manner every time. So that's why we don't really bother with that. All right, now, but the idea where F and G really play a role is when we talk about a first order reaction or a second order reaction. Okay, so if we have, say, the breakdown of a radioactive substance, okay, again, it is a reaction that is taking place over time, okay, it is taking place spontaneously, and we are still not talking about enzyme activity, okay, we are still talking about reaction rates, okay. So if we have P32 and it's just releasing alpha particles, beta particles, gamma particles, okay, and it's breaking down into something, I don't know what. Okay, but this reaction is taking place on its own, and the only thing that this reaction really depends on is the concentration of P32. Okay, so if we are looking at the rate of this reaction, which is equal to K P32, and then if we talk about F, in this case F is equal to 1. Okay, 1 because of the fact that the only thing that this rate really depends on is the concentration of P32 and nothing else. And this is an example of a first order reaction. Okay? First order reaction. But if you had two substrates coming together, okay, and then giving you a product, so if you had radioactive phosphorus.
What is 32?
32 is the number of electrons. Number of electrons. Okay? Basically it's atomic mass. Okay? Which is not supposed to be 32. Okay? Again, is anybody else confused by this? Radioactive phosphorus is called P32.
Why is F1? Why is F1?
F is 1 because the only thing that you're considering here is the concentration of the phosphorus. Nothing else.
So it's not good at 2A?
No. Yeah. So. Okay. Again, see here. The only thing that you're looking at is the concentration of just one substrate. Okay. It's breaking down into multiple products. That's a different thing. Okay. But on this side of the reaction, you have only the single substrate. It's not reacting to anything. That is why F is equal to 1. Again, you don't really need to keep in mind of where F is equal to 1. Just keep in mind if there is no other substrate that is reacting with another substrate to give you a product, there is only a single substrate or the concentration of that substrate only that influences the reaction, then it becomes a first order reaction. Okay? Now, if, in the sense that I had written the equation here, okay. Now, at this point, the rate is equal to A, and K, B. Okay. Now, like I said, the coefficient doesn't really matter. Okay. All you need is a certain concentration of B, which will give you the product. Okay. In this case, the concentration of A is important, concentration of B is important. Okay. This is defined as a second order reaction. Now, in a second order reaction, two substrates are coming together. Okay. Or the concentration of both the substrates is important, okay, for the formation of the product. The concentration of two substrates is going to influence the formation of the product. Okay. That is what defines a second order reaction as opposed to a first order reaction. Okay.
So in this case, the F and G do not equal the coefficients that are
No.
in front of.
Doesn't really matter. Okay, maybe if this was say 3 or maybe a different number, okay, then yes, we would have put the coefficients there. Again,
If they're different?
yeah, if they're different. Again, if they're 2A, 2B giving you the product, okay, it means that the product requires 2A and 2B. But what it really means is that A and B together can also just react. Okay?
The
That's why.
concentrations are the same, so it doesn't
Yes.
matter. If they're different, then you're
Exactly. All right. Now, just keep these things in mind. Basically, the whole thing that you need to, the only thing that you need to carry from all this graph is K. Or where does this rate constant comes from? Okay, or what is K? Because pretty soon you'll realize we'll be using a lot of this K1, K2 in the definition of enzyme activity. Okay, just keep in mind that the rate of a reaction is directly proportional to the concentrations of the substrates. Okay, and since it's a proportionality sign, when you put it into an actual true stoichiometric reaction equation, you need to give a reaction constant, which is K. So rate is equal to, not proportional now, is equal to K into the concentrations of the substrates. And K is the reaction constant. Okay? Or the rate constant, I'm sorry. Alright. Now, enzymes are binding to substrates and the reaction is taking place. But the major question is, why do enzymes bind to substrates?
They're made to go in there,
They want to and they're made to.
they're like a
Very
key,
philosophical
a key
concepts.
for a lock, and the key wants to go in the
Okay.
lock.
All right. So is that the lock and key model the only model? Is there any other model for enzyme binding to substrate?
Induced fit.
The induced fit model. What is the induced fit model?
Substrate.
And how is it different from the lock and key model?
Does the substrate like change conformation when the enzyme binds? Other way around?
Yeah.
Okay. Now, so the initial model, which actually is true in fact, all of the enzyme catalyzed reactions is what we define as the lock and key model. So there is a lock. Each lock has a unique key. The key is supposed to fit into the lock, and then when you turn the key, the lock will open. So the idea is that an enzyme has a very specific structure, and the substrates. So the the activation side or the reaction side of the enzyme has a very specific structure in the three-dimensional protein. And only a specific substrate can fit into that reaction space, and that is why you can consider the enzyme to be a lock and the substrate to be a key. Only two specific locks and keys will fit together. Okay. Now this is basically a very arcane concept now. Okay. And what is considered to be more appropriate is the induced fit model. Okay. Or that the three-dimensional structure, okay, is induced to fit the substrate. Still, a specific enzyme will only react or will only bind to a specific substrate. Okay? But the fact is that the activation site or the reaction site where the substrates are supposed to bind, or you can also call it the binding site, where the substrates are supposed to bind, as soon as they come in and are in contact with the enzyme, okay, the three-dimensional nature or the three-dimensional structure of the enzyme changes. Okay? Or what we define as a conformational change. There is a conformational change in the structure of the enzyme, which then is induced to fit the whole substrate. Okay? So, if you have